So we're going to continue talking about graphs of equations. And we're going to start today by talking about symmetry. So a graph can have three different kinds of symmetry. It can be symmetric about the y-axis, meaning if you fold the graph paper along the y-axis, the two halves would lie on top of each other. The y-axis is like a mirror. It can be symmetric about the x-axis, so the x-axis is like your mirror. Or it can be symmetric about the origin, which is the toughest one to see in terms of a mirror. But if you think about it in terms of folding, if you fold over x and then fold over y, so you like fold it in quarters, then the two pieces of the graph will lay on top of each other. Okay, so those are a few examples. So here the tests for symmetry all come from this picture. Okay. So there are algebraic tests for symmetry that we're going to learn, but they all are built from this picture. So these 2 points right here, this is my original point. The point that has y-axis symmetry is the same height as the original, so it's going to have the same y-coordinate, but opposite x-coordinates. One's positive and one is negative. So 2 points that have y-axis symmetry have opposite x-coordinates, same y-coordinate. 2 points that have x-axis symmetry, to get to both of these points, you go to the right the same distance, so they both have the same x-coordinate, but then one goes up and one goes down, the same amount, but one goes up and one goes down. So this one has a y-coordinate of y, and this one is a y-coordinate of negative y. And then for origin, if this is your original point, x comma y, we went right x, up y to get to it. This point that has origin symmetry is the same distance, but left and down. So we go left x, down y to get the point that has origin symmetry. So the tests for symmetry have to do with replacing one variable with its opposite and seeing if you get the same y or the same x. So the test for y-axis symmetry, we're going to replace an x with a negative x and see if you still get the same y. The test for x-axis symmetry, you replace y with a negative y, see if you get the same x. And the test for origin symmetry, you replace both of them, the x with a negative x, the y with a negative y, and see if the equation remains the same. So this is the summary. A graph is symmetric about, and then we have the three options, if its equation is unchanged when. So if we replace x with negative x and the equation is unchanged, y-axis symmetry. Y with negative y and the equation is unchanged, x-axis symmetry. If we replace them both and the equation is unchanged, we have origin symmetry. So here I'm going to demonstrate the algebraic test for symmetry for this particular equation, y equals the absolute value of x. So I'm just going to start by writing down the original equation. And to test for y-axis symmetry, you replace x with negative x. So I'm going to do my test. In the equation, replace x with negative x. But what is the absolute value of negative x? X, right? And so you see my equation remains unchanged. Even when you replace an x with a negative x, you get the same equation. Unchanged, therefore, 3 dots in a triangle means therefore. Therefore, we have y-axis symmetry. So we replace x with negative x, get the exact same equation, so we know we have y-axis symmetry. All right. Now we'll do an example where we have x-axis symmetry. So I'm looking at the equation y squared equals x. Start by writing down the original equation. And then the test for x-axis symmetry is to replace y with negative y. So here, instead of a y squared, I'm going to have negative y squared. Square the opposite of y. But what do you get when you do negative y times negative y? You get a positive y squared, right? So this is y squared equals x. Equation is unchanged. Replacing y's with negative y's doesn't make any difference. So I have x-axis symmetry. And then the last one, do an example of origin symmetry. I'm going to look at the graph y equals x cubed. And to prove that it has origin symmetry, start by writing down the equation. And then I'm going to replace the x's with negative x's and the y's with negative y's. And I want to see if my equation is unchanged. So instead of a y here, I'm going to write a negative y. And instead of an x here, I'm going to do a negative x and cube it. So I get negative y equals negative x cubed. That's negative x times negative x times negative x. What does that come out to? It's going to come out negative. It's going to be negative x cubed. And negative y equals negative x cubed. Is that the same or an equivalent equation to the original? It's the exact opposite, which makes it equivalent. Yeah. Two equations are equivalent. Imagine adding x cubed to both sides and adding y to both sides. Then we would have x cubed equals y, which is equivalent to this guy, right? Or multiply both sides of this equation by negative 1. And we get negative 1 times negative y is y. Negative x cubed times negative 1 is x cubed. And I have the same equation. So in that one, I had to do a little bit of manipulation to show that what I came up with after I did the replacements was in fact equivalent to the original. It didn't look the same, so I had to do a little bit of monkeying around to see if I could make it look the same. Okay, so using the algebraic test for symmetry, I want you to test each of these equations for each of the three kinds of symmetry. Okay, find out what kind of symmetry each of these three has. Okay. Work on it in your groups. I will come around and help if you need it. So replacing x with negative x, I get negative x equals y to the fourth minus y squared. So does it look like the original equation right now? Can I do anything to make it look like the original equation? Legal equation moves. Multiply both sides, add to both sides. No. I could try. So right, the problem is that I have a negative on this x. And in the original equation, it's not. So I could try to make it positive by, say, multiplying both sides by negative 1. But when I do that, negative 1 times negative x gives me positive x, so I fixed that. But then when I multiply the negative 1 to the other side, I get negative y to the fourth plus y squared. And now I've messed up the signs on the other side. So there's nothing I can do to make this equation look like the original. So I would say no, no y-axis symmetry. However, in the middle one, if I replace the x's with negative x's, I get negative x squared plus the absolute value of x. And negative x squared means negative x times negative x, which is positive x squared. Oops, negative in there. And the absolute value of negative x, which is also the absolute value of x, right? The absolute value of x and the absolute value of negative x are the same thing. So that is the exact same equation as my original. So yes, y-axis symmetry exists there. And then in this last one, replace the x's with negative x's, and I get negative x squared y squared plus negative x times y equals 1. The negative x in parentheses squared means negative x times negative x, which is positive x squared. So I get x squared y squared. Negative x times y is negative xy, because I have one negative and one positive, equals 1. Is that my original equation? Any way to make it my original equation? Because I'm off by one sign, and my only trick for changing signs is to multiply both sides by -1, but that changes every single sign, and I only am off by 1. So this is a no for y-axis symmetry. So that should make the process a little bit clearer, I hope. So when you do the x-axis tests, remember you replace y with negative y. So see which one of these has x-axis symmetry. Pick key points. And for y-axis symmetry, take the opposite of every x coordinate. For origin symmetry, take the opposite of both. So 3, -1 becomes -3, +1, which is right there. All right, so that's a good place to stop. We will pick up with learning about the TI graphing calculator next class. So if you have not yet procured some way to graph stuff, get that.